Recording? Okay. Hey, Chem 30. I'm just going to close the door here. Don't need to stop it. Okay, so I'm going to continue on with, I'm going to finish up this discussion on polyprotic entities. And we are going to start discussion on titration curve, and then we're going to look at acid and base strength. So it's kind of a continuation of the last lesson, and then the start of a new lesson. We're actually getting down to the last important pieces of this acid-base unit. So that so I'll be done in 2, maybe 3 lectures here. So yesterday I gave you an example looking at sodium carbonate and hydrochloric acid. I'm going to give you another example here with polyprotic entities, and then we're going to draw a titration curve for the polyprotic entity. So this one says use the 5-step method to determine the net equation for each.
Do you have black pen? It's not clear, I think. Oh, it's clear. Do you have black pen? Black ink pen?
Do I have what?
Black pen. This is not clear. Oh. Do you have another color pen? Yeah, this not. I think it's good, but not very good. Yeah.
Sketch the pH curve. Can you zoom in, zoom out? Good?
Good.
Okay, thanks. And choose a suitable indicator. So here's the deal. Sulfurous acid, sulfurous, not sulfuric, is titrated with sodium hydroxide. And there's 2 quantitative steps in this reaction. All right? So when we look at the entities, so let's start with that. We have H2SO3, and we have Na plus present, and we have OH negative present, and we have H2O present. So those are my entities identified. Okay? My first reaction is sulfurous acid plus OH negative quantitatively reacts. Okay, so that's the acid to make HSO3 negative plus H2O. All right, so I need to do this in 2 steps, and remember the SO3 and the H2SO3 is polyprotic. All right, so my second quantitative step, I'm going to continue titrating the products of this first reaction with sodium hydroxide. So this ends up being HSO3 negative plus OH negative. I should probably put in the AQ for all of these. And then that makes SO3 2 negative plus H2O. And then I can make a net reaction from this. So just like I showed you in the carbonate example, we're going to cancel out whatever we see and then add together whatever's left over. So we cancel out what we can cancel, and we add everything to get a net reaction for this polyprotic titration. All right, so that's my net ionic equation. Okay, and what I can do from this is make a graph. So this is the titration of H2SO3 with sodium hydroxide. So that's my titrant, and that's my sample. So we start with an acid, and if I look at where my pH range is, it's generally going to look like that. And then volume of NaOH added. So remember, my sample is acidic, so we start with acidic H2SO3. It's going to generally look like that, okay? So I have H2SO3 present here, and then that's my first equivalence. So there's no H2SO3 left. And then we'll have HSO3 negative here and OH negative present. And then that's my second equivalence. So there's no HSO3 negative left. So after this will be CO3 2 negative. Sorry, SO3 2 negative and OH negative. All right, so I need to be able to identify the entities at each, what happens at each equivalence. So what else will I have here? Well, obviously there'll be a little OH negative, Na plus as it gets added, right? So we'll have Na plus here as well and Na plus. And we know that H2O will be present. At each step. It's really understanding what happens if we can have more than one electron exchange. It's really looking at what happens at each equivalence. So when does the H2SO3, when is it present, when does it go away, when does the HO3 show up, when does it go away, and then what do we end up with through that polyprotic exchange. That's the big thing that we need to understand with polyprotic titration curves. Okay? So, I'm just going to pull my overhead up here just to summarize what pH curves tell us. Okay, so you guys can take one last look at that. All right, and okay, so let me just turn this. Okay, so what do pH curves tell us? All right, so they tell us about the initial pH of the sample solution. They tell us the pH when excess titrant is added, so when we overshoot the equivalence. It tells us the number of quantitative reactions. So if we have more than one endpoint or equivalence, we will know that we have a polyprotic entity. It tells us about non-quantitative equilibrium reactions. So we can find the endpoint, but we don't necessarily see the equivalence on a titration curve, right? So we can look at indicator changes on graphs, right? We can look at equivalence points for indicator selection, and it tells us about buffering regions. Okay? So when we look at pH curve shape generalizations, the pH at the equivalence is determined by the entities present at the equivalence point. So it depends on what we're titrating. So we don't usually make titration curves for weak acid and weak base reactions. So they're not quantitative, and they don't have identifiable equivalence points. So weak acid, weak base reactions essentially don't have really large pH changes. This is what equivalent, right? So indicators are weak base, weak acid reactions, right? So weak acid and a weak conjugate. So they don't make pHs, all right? But what we do for pH shape is we look at strong acid and strong base titrations, okay? The endpoint will be 7 here. We can have a strong acid and a weak base titration. So because of the properties of the hydronium of the strong acid, the equivalence point will be below 7. And then for a strong base and a weak acid titration, because of the properties of hydroxide, now think, right, much larger Kb than Ka. This is a much larger Ka than Kb. So for strong base and weak acid interactions, the endpoint will be greater than 7. And we can pick appropriate indicators for these when we determine our entities that are present. Okay, so notes on, let me just pull this up. Okay. So notes on titration curves. All right. Some weak acids will react quantitatively with hydroxide, so strong base. Some stronger weak acids react quantitatively with stronger weak bases, but it depends on the distance between the weak acid and weak base on your acid-base chart. So the further apart they are on the acid-base chart, the more likely the reaction will be quantitative, because there's a larger difference in Ka and Kb. So your basic rules, however, though, so these would be some of the exceptions that I'll point out. Strong acid and strong base reactions are quantitative, and they have a pH at 7. Strong acid and weak base quantitative reactions, their pH equivalence is less than 7, and weak acid and strong base quantitative reactions are greater than 7. Polyprotic entities produce sequential reactions and titrations. The first reaction will be quantitative, but the reactions that come after it, because they have weaker Kas and Kbs, might not necessarily be. It depends on the amount of titrant that we add, and I pointed that out yesterday. So there are questions on titration curves on page 762, numbers 11 through 15. Okay, so let me give you an example. I'm just going to cover that up. Looking at these relationships between strong acids and weak bases and vice versa. Thank you. Okay, so examples of titration curves. Write the net equation. Sketch the curve. Indicate the relative pH at the equivalence point. and choose an indicator and indicate the entities present before, at, and after each equivalence point. Okay, so my first example is going to be sodium acetate titrated with HCl. Okay, so first thing I'm going to do is identify my entities. So I've got CH3COO negative, I have Na plus, I have H3O plus because that's a big 6 acid, and I have Cl negative and H2O. Okay, now that's going to be my base, and this is going to be my acid. So when I make this equation, we have H3O plus CH3COO negative, and that makes H2O plus CH3COOH. All right, so that's a weak base and a strong acid. All right, so when I make my, I'm going to put my titration curve over here. And this is sodium acetate titrated with HCl. Okay? So there's 7, 14, and 1. So this is a strong acid and a weak base. So the pH is going to be closer to 7 when we initially start. And then when I make my titration curve, the equivalence is below 7. Okay? So equivalence is below 7. Okay? So pH should be less than 7. So I need to show that on my graph. All right, and I should pick an appropriate indicator. And where do I need my data booklet? You go. Thank you. Okay, so if I look at my acid base chart on page 10 of my data booklet, right here, I'm going to pick something that has an endpoint or a color change slightly lower than 7. So below 7, so bromothiamyl blue turns yellow, all right, and is permanently yellow after a pH of 6. So I'm going to pick bromothiamyl blue. I could have also picked something like chlorophenyl red. Even methyl red would have worked here because these are all slightly below 7. But bromo blue will be the first one that changes. So my indicator here will be bromothiamyl blue. Okay, but the other options wouldn't necessarily be wrong. They just wouldn't necessarily be as accurate. Okay, so I'm going to draw what my entities are. So before the titration, at equivalence, and after equivalence. Okay, so what do we have present before? Well, we have Na plus, we'll have CH3COO negative, and there'll be H2O. Okay? And there'll be some CH3COOH because of equilibrium. So this is a weak acid, weak base equilibrium system that exists before the titration. Can you see that? Okay. So weak acid, weak base that exists before the titration. All right. Now, at equivalence or at the end point, all you have are products. All right. So there's only going to be that. Okay. So we'll have Na plus because it is a spectator ion. There's no hydroxide because the hydroxide is completely neutralized. The CH3. There's no H3O plus because the hydronium has been completely neutralized by the acetate present. So NH plus CH3COOH, and then you'll have H2O present, obviously. Now, after equivalence, there's not enough of the acetate ion to take the H3O plus out of solution. So after you'll have H2O, CH3COOH, but H3O plus starts to build up, you'll have Na plus, and you'll have Cl negative present. Okay, so with the weak base and the strong acid, the equivalence will be below 7. All right. Let's look at the next one I want to give you. So the next one is, 2 is CH3COOH with NaOH. Okay? I'm actually just going to leave this graph up. So this will be with NaOH this time. And I'm going to have to erase this. Okay, so what do we have? We have acetic acid. So this is on my acid-base chart, right? So I don't break that up. I have Na plus, OH negative, and H2O. So this one is CH3, COOH plus OH negative. And what this makes is, right, that's the acid, this makes H2O plus CH3COO negative. So this is a weak acid and a strong base this time. Okay, so when we make the titration curve for this, this is actually going to start kind of in the middle. Here it's going to be a relatively higher pH, and then a strong base is added. So the equivalence is greater than 7. All right? So what am I going to have for entities present at each stage? We'll have CH3, COOH here. You'll have H2O, and then some CH3COO negative because it'll make an equilibrium system. So that's all you're going to have there. Now, at equivalence, right, you're going to have just the products, right? So at equivalence will be the products. So you'll have Na plus, because we've been adding sodium hydroxide. You'll have H2O. And you'll have CH3COO negative there. Now there won't be any OH negative, and there's not going to be any acetic acid or the CH3COOH. Now after equivalence, this is where the base starts to add up, right? So OH negative, CH3, COO negative, H2O, and A plus. Okay, so those are our titration curves for weak acids and strong bases, and strong acids and weak bases. Okay, so that's the second example right there. All right, just before I end this lecture, I'll give you the next part is going to talk exclusively about buffers. So I'm going to end this with one more polyprotic example, just so we can kind of shore this up. All right, so let's say we have sodium carbonate titrated with HCl. Okay, so we have a weak base and it's polyprotic. And we have a strong big 6 acid. So first thing we need to do is identify the entities that are present. Okay, and let's say this goes in 2 quantitative steps. Okay, so this is not sodium. So the one thing I want to stress here is this is not sodium hydrogen carbonate, it's sodium carbonate. Okay, so this is Na2CO3, and that's plus HCl. So that's a really easy thing to miss. All right, so entities present, Na plus, CO3 2 negative. That's going to be hydronia, it's a big 6 acid, Cl negative, and H2O. And there's 2 steps. All right, so this is my strongest base, and that's my strongest acid. So we have CO3 2 negative, titrated with H3O plus. And that's a quantitative step. That's going to be HCO3 negative plus H2O. Okay, so this is a product of if you have calcium carbonate. If we have acid rain, calcium carbonate, right, so CaCO3. So I could do this with calcium carbonate as well. This would be a reaction from acid precipitation, right? So if we have acid rain falling due to fossil fuel emissions, making sulfuric and nitric acid in clouds, the acid could fall onto calcium carbonate limestone bedrock and degrade it. We also use calcium carbonate to neutralize the effects of acid rain. Okay? Just so you're aware. So this is a very common reaction that you would see in nature with acidity. 5 minutes?
5 minutes.
5? Okay. All right, so let's get this done. So that's my first step. My second step is going to be, I'm going to take this, right, HCO3 negative, and I'm going to react it with hydronium again. Okay, and this makes H2CO3, so carbonic acid plus H2O. This is the carbonic acid buffering system in your body as well, by the way. Okay, so CO3 2 negative plus 2H3O plus is going to make H2CO3 plus 2H2O. So that's my net equation from this polyprotic reaction. And when I make my curve, okay, so Na2CO3 titrated with HCl. I'm going to have two endpoints, right? Okay, and that's my first equivalence.
No,
And that'll be my
there's
second.
no battery. No,
What was that?
only 27 seconds.
27 seconds. Okay, so first equivalence, and then, right, entities present, CO3 2 negative, HCO3 negative is your main entity there, and then after this is H2CO3. All right, and that's it for this section of the lesson. Okay, I'm just gonna sign off now. Thank you.